So if you, when you breathe out and there's moisture in your breath, do you know how long those water droplets will can stay in the air under perfect conditions?
Do you not?
3 hours.
Wow.
Perfect for the droplets, that is. You know the actual distance that they can travel?
A long way.
I think we're around 8 meters, basically, goes to this classroom. I'm glad that I did not know this information before.
A lot of the important knowledge in life is best left unknown.
There are times.
Ignorance is bliss, as they say.
All right, so I got a north end and a south end of a magnet. So my magnetic field is traveling this way. And into this, I will introduce a loop of wire that I can spin. Now, realistically, it's not a complete loop. I guess I probably should have drawn that bigger. But my wire requires the door to be closed. And so these down here would actually be connected to something which would then go out. This is basically power plant generation or electricity generation. And I'm going to spin this at some angular speed of omega. So, where's my hula hoop? Thought I'd seen it recently. Oh well. All right. One last scan for it. All right, so we will assume that there's a wire running around the edge of this thing and it's spinning. My magnetic field, similar to that, is going that way. What is the flux through the surface right now?
It's either really small or zero, right?
Okay.
Because it's the same direction.
Let's be careful about the wording there.
Okay.
You said what's going this direction?
The magnetic field.
Right, so it would probably be pretty close to zero because it's just this length or width
Yeah.
that has the magnetic flux.
Right, okay. So we'll assume it is zero. So if we just think about just the surface here. What is the formula for, I might have just said electric flux, I meant magnetic flux. What's the formula for magnetic flux?
It's B dot A.
Okay. So what is the direction of the area vector?
Right hand rule, right? It's gonna be.
Not for area vector. Area vector is simpler than that.
Is it just like perpendicular to?
Keep going.
It's this way or this way?
It's one of those ways.
This way.
It's that way or that
Or it
way.
doesn't matter.
It's one of those. Yeah, that was not a trying to lead you into one of them or the other.
Okay.
You pick one and you live with it. All right, so my area vector is that way, my magnetic field is that way, they're perpendicular to each other. Dot product is zero. So that's the magnitude of the magnetic field times the magnitude of the area times the cosine of the angle between them.
If you turned this plate this way, that works, where the, area vector and the magnetic field are going in the same direction, then it would have magnetic flux, correct?
Oh, absolutely. That'd be your maximum magnetic flux.
I just remember the demonstration you did with a sheet of paper in the other classroom. You had like a sheet of
Oh.
paper and then you like moved it.
Yep.
Yeah.
The exact same thing going on here. I think that was the electric flux at that point?
Yeah, electric
Yeah.
flux.
Exact same concept. All right. So as I spin this, I have no flux, maximum flux, no flux, maximum flux or minimum flux if you want to consider it, because my area vector is coming out this way. Why is that different than this?
Because it's in a different direction of the magnetic field. But I don't really understand why.
So-
Because cosine, would it be like cosine 180?
Yes, which is,
1. Wait,
-1.
yeah.
and to nitpick that, the spirit of what you said, absolutely right. Nitpicking it, what is the cosine of 180? And why is it not -1?
Because we can't have a negative area?
Nope, not an issue with that. The negative is just a direction thing.
Why can't we have a negative cosine, or why can't we?
Why is cosine of 180,
negative?
which is what I heard you say, not -1?
No idea. I just think of the unit circle and I'm like, okay, it's over here. And that's -1, but I'm not sure why it's not.
It's a unit thing. If you say 180, the angle is 180. What is the unit, what are the units?
Degrees?
If you don't say it, what are the units?
Radians?
Cosine of 180 radians is not -1. So again, the spirit of what you said, absolutely right, 180 degrees.
Okay.
All right, so as it spins around, I'm gonna constantly have this change in the magnetic flux. So what I care about is the change in the magnetic flux with time. Because that's gonna tell me the voltage here. So my EMF. And yeah, we'll just stick with one loop for right now. So my magnitude of the magnetic field and my magnitude of the area are not changing. These two are constants here. And I'm just gonna represent these by just dropping the vector symbol.
Question, why is EMF equal to the negative change in magnetic flux?
That's sort of a philosophical question there. The negative is indicating that whatever the induced voltage is gonna try to counter the change.
Oh, okay.
That's the whole Faraday-Lenz's law.
So so the voltage or the EMF has to counteract the magnetic flux?
The change in the magnetic flux.
Okay, so that's why it's negative.
So if the change is positive, my voltage is negative, indicating that the voltage is gonna try to lower it. If my change is negative, then my voltage is positive, indicating that the voltage is gonna try to boost it back up.
Okay, that sounds important, so I need to, okay.
Yeah, that's when I got on the table and I dropped the magnet down the copper pipe.
And it took longer.
Yes,
Okay.
that's the impact of the negative sign.
Okay.
Some claim it's the contribution of Lentz to Faraday's law.
Oh, I remember, okay. I had it written down, but I just didn't see the negative, now I see it. That's why I asked you, because
Okay.
I saw it and I was like, where's the negative sign? So thank you.
Yep. So, since these are two constants here, times the cosine of theta, theta is not constant because, again, for those who came in a little bit late, I've got a wire running around the edge of this, pretend, and wire running around the edge of it. Area vector we're establishing is in that direction, the same side as the disk here. And as it spins, my area vector is constantly changing directions. The magnetic field is going to your right, basically, same direction as indicated right there. So the angle, this theta here, the angle between my magnetic field and my area vector is constantly changing. So it is a variable. So this becomes the negative change in BA cosine theta over change in time. And anything not changing, I can just factor out. So this becomes negative BA change in the cosine of theta over the change in time. So if I plotted cosine of theta and time, what does that function look like? All right, so starting at the, where?
Gosh.
Not at the origin.
Yeah.
Okay. Think of the unit circle, when time is 0, or I guess we can take that theta there and change that to omega t. That's supposed to be an omega. Again, omega is how fast is the angular speed.
Oh, okay.
It's just speed times time. Angular speed times time is angle. When time is 0, what's the cosine?
1.
Yeah, so we start here. So it starts at whatever the peak is. So we're starting it as if time is equal to 0 at that point right there. Again, magnetic field shooting that way. And then it starts spinning around. This change in cosine over change in time, that's just the slope of this. Change in y over change in x, if you want to use math terms. So this is just the slope of this. So let's plot the slope. Where's the slope equal to 0?
At the bottom?
So here?
Yeah.
All right, one down. Are you getting thrown that my drawing is not perfect?
It's also 0 at the peaks.
Yeah.
The-
Peaks also. And so, all right, we established 0, so it's gonna be at the peaks and the troughs, wherever it sort of bottoms out or tops out. In between my first 0 and the second 0, what can you tell me about this slope here?
That is decreasing? It's decreasing?
The slope, well, it depends on what you mean by decreasing. All right, my slope is 0 there, then it becomes more negative, and then it becomes less negative, so at which point are you considering that decreasing?
From the interval of the first, time period to the second time period?
Oh, the entire time?
Yes.
I would not say it's decreasing the entire time. It might be just a matter of you did not word it the way that you meant to. Anyone else want to join in? Again, it looks like it's still up to you. So when you say decreasing, because right here my slope is 0, my slope is 0.
Right.
If you're decreasing from 0, what does that mean?
It means that you will be going in the negative direction.
Okay, so I go into the negative direction, so my slope, let's say at this point right here, it is -10, just making up some negative number. So it goes from 0 to -10, okay, so we'll call that decreasing. What about from here to here? It's going from -10 to 0, is that decreasing?
Oh, that will be increasing, so the decreasing portion will just be from, until it hits the, T line.
In this particular case, okay, so that would be, should be halfway in between, so it's gonna decrease till it gets to here, somewhere there. And then increases, okay? What about over here?
And then it's going to increase up until the next, T line, at the intercept.
Okay, horizontal intercept. All right. And then continue.
Right.
Also, another way, when I wasn't sure whether you're really talking about decreasing and then increasing the way we have it now, or the fact that you're just trying to get across the point that the slope is negative the entire time.
Yeah, I was thinking that the slope was negative the entire time, which is what I was thinking of initially.
Okay, and that's reflected here, also reflected in the way we eventually came around to it. All right, so what is this graph?
That's this
What's
sign.
sign? Because this says
Negative
more.
sign, right?
Sorry,
Negative sign.
yeah, negative sign. So this is negative sign of omega t. However, there is something a little bit off about this. It's not actually negative sign there. There's missing something up front. So if this is 1 and negative 1, because there's nothing in front of the cosine here, I have BA separate. So this magnitude, this maximum is 1, the minimum is negative 1. What is this point right here? What is the time at which we get back to our starting point?
It's the same amount of time.
That's one full revolution.
Yeah, that's what I'm at. What is the period in essence? I have this thing spinning around at an angular speed of omega. What is the period?
1 second.
How'd you come up with that?
Because you put a 1 right there. I thought.
What, right here?
No, where you put time down, like, yeah. Right.
Oh, no, that's not supposed to be a 1 there. I think that was just a mark.
Oh, okay. The period is the same, but I think you're saying that something has to go in front of sine, which makes me think that the sine graph is going higher, like it peaks at higher than 1 or lower than 1, and it,
Okay.
yeah.
Yep, it will peak higher than 1 or lower than 1. Well, actually, it might peak at 1 also. It depends upon one factor here. All right, so let's think about it this way. We start off in this position right here, as indicated by the fact that we're starting out at a maximum. It spins around with an angular speed of omega. We assume that omega is constant. Oh, let's do a flashback here. You're about to impress me. Someone's going to impress me. As this thing is spinning around like this, what is the direction of the angular velocity? Anna?
Is it up?
It is. All right.
Fingers.
It would have been more impressive if you had put the question mark in there.
It had to be there. That's
Okay.
how it felt.
Okay, next time, bluff. So, as it's spinning around at constant angular speed, and angular velocity for that matter, what is the angular acceleration?
Oh, dang it.
There's an A, right?
0. Right?
Yeah, the question is not existing the same as 0?
Oh yeah, because it's moving constantly, so there's no acceleration.
So let's go back to the angular cake formulas. Let's see, we got delta theta is equal to omega I t plus 1/2 alpha t squared. If my angular acceleration is 0, that term drops out. So what I'm just left with is this. If I'm looking at how long it takes to go all the way around once, yes?
What is alpha again?
Alpha is angular acceleration.
Okay, thank you.
It's radians per second squared. So if I'm looking about the time it takes to go around once, in other words, the period, so the period I'll represent by a capital T. My initial angular velocity is the same as my final. I'm just gonna write omega. Capital T. What is the angle it goes through?
360 degrees,
Or in radians, because we're cool.
2 pi.
So my period is 2 pi over omega. So this time right here is 2 pi over omega, 2 pi over omega. And I assume that's what you were saying, Brooke, when you said it's the same
Yeah.
earlier. All right. So if I take a function here, so if omega is 1, so 1 radian per second, it takes, my period would be 2 pi. In other words, my cosine graph would look like this, and that would be 2 pi. And then suddenly I make omega 2 radians per second. So this is omega is equal to 1 radian per second. And if omega is equal to 2 radians per second, what does that mean physically as far as the spinning goes?
Twice as fast.
Say it again?
Twice as fast,
Yeah. So what does that tell you about the period?
half as much.
Yeah, which is also indicated over here. If omega becomes 2, then my period is just pi. Which means that this graph now is going like that. So think about this red graph here, and then think about the blue one. What does this tell you about the slope? How does the slope of the blue one compare to the slope of the red one?
It's steeper because the frequency is, omega like basically a frequency here?
It's angular frequency. In this context, it's angular speed, but once we throw it into the equation, we suddenly call it angular frequency.
Okay. Is the slope going to be half? Or,
You're saying that this slope is half of this slope?
that doesn't make sense. We know it's we know it's greater, because, is it double?
It would be doubled.
Yeah.
And so, and it's doubled because omega is equal to 2. If omega is 3, tripled. In essence, what's happening here is an omega gets stuck out front. For those who've had a little calculus, you'll look at that and go, yeah, of course.